Okay, hello, my name is Jacek Gębala. I'm a PhD student working with Professor Tomza right here at the University of Warsaw, and I'll be talking to you about the free body collisions. So our motivation for the work in ion atom systems were the publication in Nature that showed the cooling to ultracold regime, barium ion immersed in gas of ultracold gas of spin polarized lithium, where several ion losses were explained using the collisional dynamics, two-body collisional dynamics, so through calculation of Feshbach resonances, including spin-orbit coupling, although not to the highest order. And however, like an order of magnitude of certain ion losses were not explained, and it is the motivation is that the free body theory could better explain what is going on, if there could be any effects that affect the recombination rate in these kind of systems. So just to give you like a heads up how we even approach the free body problem theoretically, we begin by thinking about free particles, which in Cartesian coordinates are described by 9 degrees of motion, and we are trying to simplify the problem, so mathematically simplified Hamiltonian by reducing the number of degrees of freedom in the system. And obviously the first thing we can do is to get rid of the center of mass motion, which reduces 3 degrees of freedom. However, that's not all, because we need to remember that free particles, they define a plane, so going to the body fixed frame will fully reduce the problem to with another 3 degrees of freedom. We are left with a scaling factor, which is called the hyperradius, and 2 hyperangles, which define the relative geometry of the free particles that we are considering. Therefore, the way we can solve the free body problem in quantum mechanically is first to, similarly to the two-body case, introduce a basis set, the adiabatic basis set, where we find the eigenfunctions of the hyperangular part of the Hamiltonian, and then resolve the dynamics or the coupling between different hyperradii by solving the hyperradial Schrodinger equation. That's what we do. So here's like a general picture of how the solutions or the effective potentials might look like in the free body problem. So we see that at long range, for large hyperradii, we resolve the rotational structure of the two-body molecules, and plus the energy of the atom. Above the threshold, we get the continuum channels or free unbound atoms, and the free body effective potentials, similarly to the two-body effective potentials, they support free body bound states, which can be resonant or simply bound simply bound, or they can be also resonant. I will not go into that. So here, one thing also to keep in mind is that ion-atom interaction and atom-atom interaction are qualitatively different, and the main thing we need to keep in mind is that the energy density of the bound states is vastly, or the order of magnitude bigger in the ion-atom case. This is because ion-atom interaction is long range. This one scales as 1 r over r to the 4th rather than 1 over r to the 6th, known from the van der Waals interaction. Hence, we see this plethora of ion-atom states rather than an order of magnitude less of the atom plus ion states. And we can confirm that by calculating that the most prominent factor in the total recombination rate comes from the recombination pathways that lead to ion atom plus an atom molecular channel. Here I want to present one of the results, which is the effective potentials for the barium ion immersed in lithium. And we see here I scale the molecular channels above the continuum with the R² factor, and we see kind of the interplay between repulsive and attractive coefficients, and this interplay leads to avoided crossings at large hyperradii, which lead to strong oscillating effects in the recombination. I will get to that in a second, but yeah, that is something to keep in mind. However, below is our typical rotational structure at large hyperradii. So these are two-body molecular energies plus the energy of the lithium. However, we can identify how these channels behave, and if I subtract the threshold energy and multiply it by hyperradius to the fourth, we see that at large hyperradii they behave as if it was as a 1 over r to the fourth type of interaction. However, at medium range it is 1 over r squared, which is characteristic for free body collisions. These kind of parts of the potential can support the FMO structure, the FMO states. However, at large distances, it is 1 over r to the fourth, which resembles a molecular ion interacting with the molecular ion as a whole. Okay, but here is the main result. So here are the calculated recombination rate across a range of atom-ion scattering lengths. And what we see? Well, we see the oscillations, and this effect is known. It is a Stockelberg type oscillation, which basically comes from the fact that we get in the incoming channel we get a wave function that couples to the molecular channel below the threshold, and then it can immediately scatter back or bounce back from the short range potentials, which describe the short range chemistry, and then get a phase and then scatter to the large radius. So then the atoms can scatter back. So that is, let's say, a known effect where this kind of phase that I described is introducing the oscillations in the recombination rates. At large atom-ion scattering lengths, we get your typical a to the fourth scaling, which has also been very much described in the neutral systems, and at the low scattering lengths, they average out to a constant, which is also pretty well described as well in the neutral case. However, these type of Stockelberg oscillations are enhanced, especially in neutral case. It was shown that they are enhanced whenever we get a mass imbalance system similar to our system, which is barium, which is a heavy ion, and light atoms. However, what is new and novel is the fact that we see a double structure. And this double structure, it's maybe a very light color that I use, but like the light blue color seen here is the partial recombination to the least bound molecular channel. And so our typical Stockelberg oscillation would only involve one minimum for this molecular channel. However, here we see this double structure, which indicates that there are two main distinctive pathways for the recombination, and we are still trying to understand where they really come from and how the interplay between the molecular channels, the crossing within the molecular channels takes part in that process. Just to further convince you that this is really a physical effect, well numerically resolved, here for example, these recombination rates are extrapolated to the zero temperature, and we see that across collision, when I plot the recombination rate across different collisional energies, we see that these type of oscillations are also present. So so we will extrapolate this effect to the t equals 0. And one last thing I wanted to show to really convince us that this is an adiabatic effect that I'm describing. We also resolve the free body bound molecular spectrum, and we see no resonances stemming from the free body. I mean, we see some, but they cannot describe the actual oscillations in the recombination rate because they are not placed at the exact values of the scattering lengths that we see the oscillations at. So so that's why we are further much convinced that this is an adiabatic effect. And with that, I would like to thank my collaborators. This is a work we've been doing with Professor Jacek Ge, who is my supervisor, as well obviously with Professor Michał Tomza, and our molecular systems group here in the Faculty of Physics. Thank you.
Thank you, Jacek. There is one question. Yeah, thanks for the interesting talk. So how do the three-body recombination rates compare to the elastic scattering rates?
Okay, that's interesting. Yeah. So we checked also I'm not sure, we also checked the atom molecule relaxation, and they are similar order related coefficients. So they will be important in the scattering process, the free body recombination. I'm not sure. Yes, because if I multiply by the typical density, like 10 to the 12 centimeters to the -3 or whatever, and we see that both the recombination and the elastic might be similar in order of magnitude. So,
Okay, thank you.
Okay, yeah, that's another question.
So you said you observed an Efimov bound states for a heteroatomic system?
no, I did not say that.
Okay.
All I said is
Just
that
to be
we
clear.
see free body states. They are they are not resonant, and they cannot describe the recombination oscillations that we see. Hence, we deduce that these recombination oscillations stem from the adiabatic effect, like Stuckelberg oscillation. What is very interesting is that we see a very well resolved double structure within the Stuckelberg oscillation, which would provoke us to think that maybe there are two pathways of recombination that overlap. But I don't want to get much into detail into that while answering your question. But what you said is that about the Efimov states, we do not really see. We see free body bound states, but they cannot describe the recombination oscillations.
And the lithium is bosonic? Or
Yeah. Sure.
they're all neutral, right?
I mean, we calculated with barium ion and the lithium spin point.
Okay.
So
Nice lecture. So.
Are there any other questions?
hello. Yes.
Yes, so very interesting talk. So I wonder what would happen if you had two isotopes of lithium, and that would maybe induce a tiny dipole moment and change the interactions. Do you have any idea about how this would influence?
Yeah.
the results?
I mean, it's definitely a very interesting way to go forward, but we haven't yet done this. So I don't really know. So.
Good. Any other questions? Not? Let's thank Jacek.